So let's take a look here. Our tools to underline. What's going on here? This is, so there's a notice, continuous exponential decay. Continuous exponential decay. Do not round until the end, then get to the nearest hundredths. Okay, we'll just put it all in. So the mass of radioactive substance follows a continuous exponential decay model. What you just want to remember from this, what is continuous exponential? Either decay or increase, doesn't really matter. Continuous exponential is always PERT shampoo. Like I said, it was a big advertising thing, PERT. And what is PE to the RT? Even if you don't know what the shampoo is, I guess, PERT. But they had a lot of advertising. Everyone knew what PERT was when I was a kid. And that's going to give you your amount, right? I'll put A, accumulated value or whatever. The only thing is when it's exponential decay, the rate, since it's a decay rate, it's going to be a negative. So we're going to think of it, it's decaying. It's a negative percentage, and then turning it to a percentage, you move the decimal over 2. Why? Because you're dividing by 100. Take this divided by 100. We're going to get our rate. Our value for R is going to be 0.031 with a negative in front because it's decaying. Okay. Find the half-life of this substance. That is the time it takes for 1/2 of the original amount in a given sample for the substance to decay. So we know what we're looking for is T. We don't have that. The thing is they didn't give us P either, and so we think, what did I do? Well, whatever we start with, we could think of it as 100%. Let's do this. We got 100%. We know what the rate is, 0.031. We don't know what the time is, so we'll put our T there. But we know what we're looking for is when will we have half of that? Well, half of 100 is 50. And what you'll see is as we go to solve this for T, divide both sides by 100. And 50 divided by 100 is 1/2. So you could have also jumped to this, say that whatever we're going to have, it's going to be when we have a half left. And we started with 1, and now we have a half. I just think it's easier to think we got 100%, right? Using that 100. Now, how do we solve this? One way to explain is you take the natural log of both sides. I like to just explain this as we're going to do the log dance. The log dance. So this is the base. E is the base. So we have a log base E. Notice the E and the exponent are together on this side. So they're going to separate. If the E comes over to this side, that means that the exponent has to go here, and that the 1/2 goes into the logarithm. If you remember, the log base E is also written as ln, which is what we will use on the graphing calculator key. But before I do that, since I'm going to have to rewrite it, let's just, how do I solve for T? I divide by negative 0.031. Divide by negative 0.031. So we're going to have T equals, it's going to be in days, the natural log of 1/2. And you'll see that's always going to be involved whenever you're doing half-life. It's when how many days will it take until half of it is gone. Okay, and then we're going to divide that by 0.031. And so I come to my calculator, let's clear that out. I just enter in natural log 1 divided by 2, or you could put in 0.5, both will work, divided by negative 0.031. And it's dependent upon the percentage decrease, right? 22.35 days. Nearest hundredth, actually 36 days. That gets rounded up. The 5 gets rounded up. So 22.36 days. And that is it. That is it. Okay. I guess I'll show you just one other step. Again, if this made sense, you can move on. But another way that is sort of shown to do this, and it was the way I learned, but I'll be honest, it didn't make a lot of sense. That's why I came up with this log dance thing. But if you've seen it this way, maybe this will make more sense. So we've got this equation. So we're starting here. What we do is we take the natural log of both sides. You can do that because it's just like we can add a number to both sides and such. This is the way it was originally described to me. So we got natural log of 1/2. When you take the natural log of e, they sort of cancel each other out. Basically, remember, as we've been talking, the exponent becomes the answer. Natural log of e, those are going to go away, and that's what we end up with. So we end up with the natural log of 1/2 equals negative 0.031t. So see, we ended up, I'm all over the place, aren't I? We're kind of ending up with the same thing. All we have to do now is divide by negative 0.031, negative 0.031. So this is what our answer is going to be, or when we calculate it, we would get the same thing. These cancel out, just leaving us with t. But it's a sort of a different thought process. And if this side makes sense to you, maybe go ahead and do that. That works. If the log dance makes sense to you, this just kind of reorganized. To me, it's just kind of like, okay, each place has its thing, and then the calculation seems more natural. But always look for multiple ways of understanding, and then we all get to work from our strengths, what we're good at.